This kind of session is based on a hobby project where I'm using, not really AI, but I'm using machine learning algorithms to find mixes that will mix well together and creating those samples. I'll talk about how that all of that goes as I go through the presentation. A bit about myself, my name is Alan Smith. I've been writing code for about 30 years, traveling around conferences and doing courses for about 20 years. I've done lots of work with the community. I've been awarded the AI MVP award from Microsoft. This isn't about being clever or passing exams, it's just about sharing knowledge with the community. So I've been involved in organising conferences, speaking at conferences, user groups. I've helped kids at Coder Dojos learn about AI, and I also very occasionally publish something on YouTube. You can connect to me with LinkedIn. There'll be a QR code at the end. The whole interest that I got, the whole reason why I got interested with working with embedding and nearest neighbor searches and vectors and similarity and all of that stuff is a project I was working on in the it was basically an auction house, and they were aggregating together lots of auction lots. And what they wanted to do was, based on the images of these auction lots, they wanted to be able to classify the auction lots into 28 different categories. We had 10,000 images for each category, about 280,000 images, and we used Azure machine learning to train the model to be able to make those predictions. So here it's going to make the prediction of putting the lot into vehicles. That was quite a successful project. It took 5 days to implement. I arrived on Monday morning. We deployed the model into the test environment on Friday afternoon. And we took their billing down from about 4,500 euros a month to 400 euros a month in terms of what it was costing to actually make those predictions. It wasn't perfect, though. It would predict toy cars and put those in the vehicles category. So we were also looking at doing the text classification as well, use the vehicle, use the image and the text to be able to help make more accurate classifications. Whilst I was working on that project, or very close to when I was working on that project, this video popped up on my YouTube feed. Eric Bernhardsen, who used to work for Spotify, and he'd worked on working with vector algorithms for Spotify's recommendation engine. The challenge that they have at Spotify is, how do they recommend music to people? Well, this is easy if you look at classic recommendation algorithms. They basically say, well, based on what I listen to, if you listen to the same music as me, if I start listening to a new band, we'll recommend it to you. And it's all based on what users listen to and what other users listen to, and finding similarities in those trends. However, when a new band comes to Spotify, they'll put 30 or 40 tracks into Spotify. Nobody's listened to those tracks. So they can't recommend them to any other tracks because nobody's listened to them. And because they can't recommend them, they get very, very few listening stats on those tracks. So what Spotify wanted to do is to say, well, when a new band drops music into Spotify, we'll look at the sound of that music, we'll analyze the sound of that music, and does this sound similar to music that I listen to? And if it does, then it will pop up on my recommendations feed. So Eric had created something which is called Spotify Annoy. It's the world's coolest acronym. It stands for Approximate Nearest Neighbor, oh yeah. And the Approximate Nearest Neighbor algorithm, or the ANN algorithm, is something that we'll hear as we go through and look at working with vectors and embedding. And although the Spotify Annoy, this index that he created, was based on music. It was really meant to do music embedding. It works with any kinds of embeddings. And this is what really captured my interest. A section in the presentation where he was talking about he'd trained a neural network on classifying different plates of food. And what you could do is if you search for similar images to this plate of food, it comes back with these. If you search for similar images here, it's coming back with these. So it's very good at being able to do image similarity based on the actual, what's in the actual image. So I thought, because I was working on this project, this is really cool for the auction company, because what we can do is recommend similar products based on the image similarity. And many of these auction items, there's somebody who's, really interested in collecting a specific type of weird-looking brass horse sculpture. And what it was able to do is to take that brass horse sculpture, and if the bidding goes too high or if somebody else buys the item, then it would show other brass horse sculptures that look similar to that one. And because we trained the model on 280,000 images, it was really good at being able to identify the features in these auction lot items. It was so good that when you were looking at a Rolex watch, if you search for similar images, it will come up with other Rolex watches. If you search for a tag watch, it will come up with other tag watches. The logos on the watches were enough, features to be able to say that these look similar. Unfortunately, at the time, the Azure AI Search capabilities did not have the vector search, and it was quite clunky to create the Spotify Annoy. You can't just add an item to it. You've got to rebuild the index every time. So it wasn't really practical to use because they were getting, thousands and thousands of these images coming in all the time. So that had to be dynamically modified. But today, we could do it with Azure AI Search using image embedding. So Spotify Annoy. It's written in C++, but it has Python bindings, so you can use it. And I mean, I still use it as an on-premise way of being able to do vector queries. It's very, very quick, and 10 or 15 lines of Python will get you up and running with this, and it's a free download from GitHub. Now, embedding is typically used, we typically think of embedding with large language models as text embedding. And we've got these embedding algorithms such as Adder 002, and OpenAI has text embedding small and text embedding large. And what they're able to do is to take text and to generate it into a series of floating point numbers so that we can search for similar text. So if I go to the text embedding demo, I'm going to whiz to the top. This is a Jupyter Notebook, and what I'm doing is I'm connecting to the OpenAI service, and I better refresh my key because this is being recorded. And what I'm doing is I'm connecting to the text embedding Adder 002 model. So if I run that code, we're then connected. I'm now generating a few sentences. So we've got the food was delicious and the waiter was very friendly. We've got the main course was excellent and the staff were very hospitable. I'm not going to pronounce that, but that's the same thing in French and Swedish and Italian. I've even translated it into Klingon. In the workshop yesterday, we built a pizza bot where you could order pizzas, and you could actually order pizzas in Klingon. The language models would understand Klingon. So that apparently is the food was delicious and the waiter was very friendly in Klingon. And then I've got 3 sentences about embeddings. Embeddings can be used to calculate similarity between sentences. Embeddings are useful for natural language processing tasks, and embeddings are a dense representation of input text. So all of those are about embeddings, and these 2 come from one of the Microsoft courses that I teach, and I had an example of talking about embeddings and similarities. So I put those examples from the slide deck just into this demo, just to get clarification that those worked. And then we can actually get the embeddings from a text. So what I'm doing is I'm taking the zeroth, or the top one there, the food was delicious and the waiter was very friendly. I'm actually getting the embeddings for that. And we can see that the embeddings, it's 1,536. So we say that that model has an embedding dimension of 1,536. If I run this, you can see it's just a big bag of floating point numbers. Now what we can do is we can use something called cosine similarity to figure out if these sentences are similar, or figure out how similar these sentences are. And what cosine similarity does, if you remember back to school, the cosine of an angle of 0 degrees is 1.0. So if these high-dimensional vectors have the same angle, then it's going to give us cosine similarity of 1.0. They don't have to have the same magnitude, but as long as the angle is the same. So what I can do is take embeddings. If I take the same embeddings, then the angle is going to be 0, and you can see that the cosine similarity is 1.0. However, if I change the sentence to a sentence that's still in English, it's using different words, but the sentiment is the same. That means the same thing. We can see that the cosine similarity is 0.919. This is not a percentage. It's just the cosine between the angles of those vectors in high-dimensional space. But it becomes more interesting when we change the language. So if I do this, we can see that we're now comparing English with French. It's still 0.91. And then we can go across to Swedish, 0.90, and we can compare French with Swedish, 0.87. So even though we're changing the language, as long as the text has the same sentiment, we've got a similarity there. And if I go to, say, number 6, that's one of the things talking about embedding. You can see it drops to 0.68. And what we can do then is just basically plot these on a graph or generate a matrix of these. And what we can see is that the sentences that are talking about similar food, they kind of all have this green band around them. There's very similar sentiment there. The Klingon one, I don't think they've done embeddings based on the Klingon, so it doesn't understand the Klingon words too well, so that's not working. But the ones where we're talking about embeddings and what properties of embeddings, those all have similar embeddings. And the children played happily in the park, the kids happily ran around in the playground. We've got similar embeddings there. So that basically shows the maths behind what goes on with embeddings. We can also use this for searches. So what I've got is a search index where I've got questions and answers about artificial intelligence and machine learning. And if I drop to the portal, we can see what that index looks like. So if I go to portal.azure.com, I've got an instance of the Azure AI Search service here, and I've got a whole load of indexes present in this index here. And we've got the AI white papers index. It should be one of the text similarity ones. Is it this one? And if I run a query on that, oh, that was the wrong one. Sorry, I need to find the correct index there. AI FAQ vector index. That should be it. So what I've got is I've got the question and the answer for each of those questions, and in the fields, I've generated embeddings on the question and embeddings on the answer. Now, there's different ways of being able to search in Azure AI Search. You can use a keyword search, or you can use a vector search, or you can use a hybrid search, and there's various other capabilities here. So if I enter, I want to know about finance. We get the question, oh, it should have been really, I want to know about AI in finance. So let's try that, about AI in finance. And it's coming up there, what are the risks of AI in warfare? Now, this is a keyword search, and it's the 1, 2, 3, 4th option here when it's saying, can AI be used in finance? But the vector search is getting that information out here. Also, if we vary the question, I want to know about AI in the banking industry. The keyword is coming up with what are the risks of AI in warfare, but when I do a vector search on the question or a vector search on the answer, the top answer is, can AI be used in finance? So if I say I'm a farmer, how can I use AI? It's coming up with the keyword search is talking about accessibility, what is a chatbot. Third is agriculture. With a vector search, it's picking agriculture as a top one. So very often, when we're building retrieval augmented generation solutions, the users are answering questions, and they may not. When you get used to using Google, I'm old enough to have used AltaVista before Google came along. You get used to being able to understand what to put into a search query to get the answers. With a chatbot, you're writing questions. So the chatbots are incredibly good at being able to get information out. So if I take how is AI applied in agriculture, and I translate this into Norwegian, we've got this here. I can just do that to copy it, I think, and then go there. Oh, the keyword search did get it. That's weird. That's just coincidence, though, I'm guessing. But you can see the vector search is getting those, even when the language is different there. So the vector searches are fantastic. However, I wouldn't say that vector search is better than keyword search. It's a bit like saying a non-relational database is better than a relational database. It depends at what you want to do. We work at my consultancy company. We've got a customer, and they paid a data science company to build them a job search. And so what they've done is they take all of the jobs from the job list index, they embed all of the job descriptions. When somebody uploads a CV, they embed the CV and they embed the text that the user says when they would like a job. And they built this thing. It had taken months to build it, and it was using all of these fancy embedding models to do an embeddings text vector search that was going to be much, much better than a keyword search. And it wasn't giving the appropriate results. It was relating to negatives. So if I say, how can AI be used in, what was the finance one? If I just search for finance, that was a good example. How can AI be used in finance? Now, if I copy this and say how can AI be used outside of finance, the vector model is still returning how can AI be used in finance. So the problem that they had was they had like these case studies that weren't working. One of them was for a teacher who had worked over 15 years as a teacher and didn't want to work with teaching, didn't want to work in schools. They wanted a job, but they wanted to work with young people. So they uploaded their CV, and they said, I don't want to work as a teacher. I've done it for 15 years. I still want to work with kids, but I want to work outside of the school system. And it came back recommending all of these teaching jobs, because it's just doing the vector search. So they came to us and they said, can we build something better? I was free, so I spent 5 days and built something that was using keyword searches. And what we did was we took the curriculum vitae, we created, or we asked a large language model, we basically generated a keyword search, and we said, based on this keyword search, generate a query to find the most relevant jobs for this particular CV, and gave them the text CV. And then we said, based on the text that the user has entered, modify the search parameters to improve the search results based on what the user had asked in the question. And that would do a keyword search using filters. And if the user had said, I don't want to work in the teaching industry, it would set the job description on the filter of teaching to say, job description does not equal to teaching. It would just filter out all of the teaching jobs. That works much better. And it was using a keyword search, and we were using query rewriting. So I love vectors, I love embedding, but they're not always the best way to do things. It's not always better. Based on a use case, I'd say the majority of the time vectors are going to be better, but not all of the time. So that's text embedding. A bit about how embedding works. I did mention this in my workshop and in the previous session, so I won't spend too much time on it. But basically, we cannot understand 1,532 dimensions, and that's basically the maths, the vector maths that's taking place for text embedding. But we do understand 3 dimensions, and you could argue that, well, you can take colors, you can put them into a 3-dimensional space, and we've got something called cosine similarity, which is looking at the angle of the vectors. It doesn't care about the magnitude. And the cosine of an angle of 0 degrees is 1.0. So according to cosine similarity, Azure and dark Azure have a similarity of 1.0. There's no difference in those angles. And cosine similarity is usually the best mechanism for doing this. There's also Euclidean, and there's also something called dot product similarity as well. So it's just basically the maths that's used to compare those vectors. And you could argue that, well, with the Euclidean, this is the distance if you use Pythagoras to work out the actual distance in 2D or 3D or 1,592 dimensional space. That's the actual distance there. And cyan would be, more similar if you're using Euclidean. So vector searches are cool. We can take text, we can embed the text, and we can find nearest neighbors, and we get text with a similar sentiment or a similar meaning. We can also do this with images, and this was what I was planning to do with the auction house. That was what was shown on Eric's slide with the food pictures. We can embed images, and we can find nearest neighbors, and we can get similar looking dogs. Now, there is a law in the EU AI Act that says that you're not allowed to use biometric identification systems in public. I don't know if it covers dogs or not, so I'm going to run through the example and show how this works with dogs. So this is really the prototype that I built for the auction house, but I'm replacing the auction items with dogs for privacy reasons. I can't really show their data. So if I go to the similar image search, I'll whiz up to the top and we'll go through how this works. So I like writing code and working with models, so I'm importing a bunch of libraries there. I can run that code here. And what I'm using is I'm using a ResNet 18 model, and I'm building my own embeddings model to embed the images. Now that sounds really, really complex if you're a data scientist and you say, oh, I've just built my own image embedding model. It sounds complex. It's about 3 or 4 lines of Python.
What's the difference between embedding versus fine-tuning in your
Embedding is just when you take an object and you generate it into a series of vectors. Fine tuning is when you modify the behavior of a language model based on making it speak Klingon better or making it speak Norwegian better.
So if you have this data set, why embed? Why not just fine tune the model with that data? Why do you choose embedding instead?
Embedding is a way of getting the actual sentiment. In the models itself do token embedding, but it's hosting a fine-tuning model is expensive. Fine-tuning a fine-tuned model takes a long time. Embedding is something that you can do on the fly and consistent. So what I'm doing here is I'm creating a image classification model. And this is the same as the auction house. We're classifying the images into different classes. And what I'm using is ResNet 18 from PyTorch. Now, this is a convolutional neural network. It's got 18 layers, and it is the simplest one. There's also a ResNet 36, 52, 102, and 158, I think, that have the respective number of layers. And what I'm doing is I'm setting the weights of the model to models.resnet18.weights.default. So that's the default pre-trained model that's trained on a bunch of different classes to be able to classify those classes. So I don't need to train my model. I switch my model into the evaluation mode, and then what I can do is create a transform. When you take in an image, it's basically, you know, a JPEG or a PNG file. You can get the pixels on the image, but they can be different sizes. And the language models, they want floating point numbers, so you can't really send them the byte values that you've got in pixels. So this will scale the image to 224 by 224 pixels and convert the pixels to floating point numbers. And that's just a transformer. And then what I can do is go through my dogs folder. So I've got a folder of dog images. If I reveal this in File Explorer, we've got data and we've got dogs. So these are basically 10 cute photos of dogs. So what I can do is I can run that, and the ResNet image model is going to do classification on those dogs. It's the simplest model, and you can see that it understands a lot about dog breeds because the model predicts English foxhound for beagle, boxer for boxer, boxer for bulldog, and we've got German shepherd being predicted correctly. It's a bit confused about Labradors and golden retrievers, but so am I. It's got poodle correct and Norwich Terrier instead of Yorkshire Terrier. So the model is pretty good at being able to do that prediction. Now, I've got a vision classification model. I've written about 4 or 5 lines of Python, so it's really easy to get started with these vision models. Now, what I can do, if we drop back to the slides, we can look a bit how the image embedding works. If I just whiz past that. So what we do is we take an image and we generate the vectors from the image. Now, a convolutional network looks something like this. We've got lots and lots of convolution layers, and in ResNet 18 there's going to be 18 of those convolution layers. And they start out by doing edge detection. They detect edges and corners and curves and so on. And then they can put those edges together and they can detect shapes. And they can put those shapes together and detect features. And eventually, we've got the FC layer at the end, which is going to do the classification and say what it is. And these features, like in this, they're things like dog's ears, blueberries, paper cups, noses, just various things that the model can see. So to do feature extraction, if we've got these 15 layers in the model, and the model's doing classification like it is now, I can just remove the classification layer. And instead of the model predicting what is going to be in the image, it's going to output the values of all of the features that it uses to predict what is in the images. And those features can then be used as the actual vectors in the vector database. So what I do in this example, if we go back to the Jupyter Notebook, is this line of code here. So what I'm doing is I'm creating an embeddings model using the ResNet 18 with the default weights. This line of code here is going to replace the final classification layer with an identity layer that's just going to send out those values. And now I've got my own image embedding model. So if I run that code, that creates my embedding model, and I can test it with one of the dogs. And now, when we send in the image, we just get out the embeddings for that particular image. And then what I can do is I ran another process that put all of those into Azure AI Search. And this index here, if I browse back to search, this is going to be, in the indexes, we've got the dog vector index. So there's 12,300 documents in there. It's showing the sizes. When I query this, you can see that for each image, we've got the file name, we've got the ID, and the embeddings. So what I do is I just do a similar search and say, find the most similar vectors to, similar images that have the most similar embeddings to the embedding that I'm sending in, and give me a list of those files. So here, what I can do is to use it to search for similar dogs. So here we've got the dogs coming out, and I can select dog ID 0 and do that vector search. So this is the dog that I'm searching for. And these are the dog friends that have come back from that particular dog that look similar. And I can go for, say, the German Shepherd. Oh, let's go for the Poodle. I usually choose the German Shepherd, but we'll take the Poodle instead. You can see it's finding dogs that look similar to that. So dog identification works fine as well. And I thought of a really cool project. I thought, well, this is fun. Let's do it for, like, face identification. How many people saw the Terminator film last night? So my demo is actually based on the Terminator vision, and when we have conferences in Sweden, my company usually has a booth, and we usually have a cool game that's something relating to AI that we wanted on our booth. And so we were brainstorming for one of these games, and I said, let's build a Terminator. And they says, no, Alan, you're crazy, we can't build a Terminator. Yes, we can, I can build a Terminator. And the idea was to have a Terminator head and Terminator vision. And what it was going to do, I've got the prototype here. I can't really use this in a public place because it does use biometric identification, but I'll point it at myself. So if I run this, what this is going to do is to simulate the Terminator vision. So we should get the Terminator vision HUD popping up on the screen. It will probably say the location wrong. I don't think I've set the actual location to NDC AI. There it goes. It's a bit slow on this machine to start up. There's a lot of code that it needs to load. Yeah, and then we've got that. So it's saying selected target area Tekorama. Oh, this code that's whizzing by, I thought an easy way of doing that is it just grabs random Python files from the actual project, and there you go, scrolling down the screen. So that is actual computer code that runs. And then when I come in, it should recognize me. It's not doing, is it going to do that? The lighting is always terrible. Maybe I need to stand under a light for it to do that, but it's not going to get me. That's frustrating. No, it doesn't recognize me, but usually the lighting is a bit different. I don't know if I can stand under that light. And if it's going to get me there. No, it's not working. I won't fool around with it too much. But I've got a video of a demo that actually worked before I'd done the HUD stuff. If we go back to AI data, demo videos, and I run this. And this was at the Tekorama conference, sorry, the Cloud Brew conference in Belgium. And so I did actually contact all of these speakers and say, is it okay if I use your face in a Terminator face recognition demo that I'm doing? And they're all great people. It says, yeah, absolutely. And so I have got permission for these people. And the idea is that we were going to have this on a booth. It was going to do the Terminator vision. And people will be walking past. And if you're just a regular human, it says unknown human, mostly harmless. So it's doing the face detection. If it doesn't find them in the database, they're mostly harmless. But when one of the speakers walks past, it will recognize the speaker. We were going to get permission for everybody. And it uses the bio that the speaker has on the conference website, and it takes their skills, and ChatGPT generates a humoristic reason as to why that particular speaker, but based on their technical skills, can be a threat to to Skynet. So you can see here it's generating these humorous descriptions. Martin, it's not perfect. You can see it classifies Martin as Alexander and then picks him up as Martin. But he brews his own beer, and that's mentioned in his bio. So he can get Skynet drunk on his home brewed beer and delete their whole system organization with his .NET web technologies whilst they're inebriated. And I thought this will be fun. And then the EU AI Act comes along and says, no, you can't do that in a public place. So I've got the demo. I use it at conferences and stuff. It's fun, but unfortunately, we're not allowed to use that one publicly. I think that I'm just joking here. It is important that big organisations can't use biometrics in public places. It's just unfortunate that my fun demo fell into that category. The fun thing was I built that demo in Malmö. I was doing a course down there, and I was in O'Leary's in Malmö having a beer and just started on this, and contacted the speakers, and they said, yeah, okay. So I was actually coding the demo on a crowded train from Malmo up to Stockholm, and you're normally looking at the person on the table across, and they're doing a PowerPoint presentation. Oh, that's interesting. But I'm building a face recognition system and testing it, and I'm thinking I should have worn the black suit and the earpiece and the sunglasses. It would have been fun. Yeah, so the actual process that you want to do, I mean, this is what we were proposing for the auction house, is that we take the image lots, we embed them, we stick them in Azure AI Search, and then you can just search for similar images using AI Search. Face embedding, this was doing the same. I'm using Spotify Annoy because I want this to run locally on premise. I also don't want to put biometric information about people's faces into the cloud, because that may be breaking a few of the other laws that we've got. So it's running Annoy local premise, and I'm just doing the face identification like that. It's fairly easy to build. So the next thing that I kind of moved on to was the original use of Spotify Annoy, which was to find similar sounding music. And I kind of got into working with music and looking at DJs and how DJs work. The software on the screen is something called Recordbox. I'll talk about that later on. Before I go any further, I'm going to share my opinions on AI and music. Because I've been checking up so much music-related stuff, my YouTube ads are continuously bombarding me with AI in music type solutions, where you can just generate vocals, you can generate chords, you can generate keys, and stuff like that. I really hope that AI does not take over the music industry. There was a famous DJ who was saying, yeah, we're going to get AI-generated DJ sets, but who's going to go to a nightclub and there's going to be an AI that's just generating the music instead of somebody jumping up and down, shouting and waving their arms in the air? You need that human interaction. And the reason why I don't think AI will replace musicians is drummers. I did a bit of research before this session. The drum is 7,500 years old. It's the oldest musical instrument. And if you're running a band and you've got to do a world tour, the last thing you want to do is to have to set up a drum kit on stage, the acoustic drum kits. You know, guitars, keyboards are fairly easy to set up, but a drum kit, you've got to set all of that stuff up. You've got to put all of the microphones in there. You've got to tune the drum kit. You've got to ensure that there's no rattling. You've got to protect the sound from all of the drum microphones, from all of the other audio effects. It's a real pain to set up. And you need a drum technician to take around as well as your drummer. So that gets expensive. And taking a drummer can cause problems as well. The Who did a tour of the US and they took Keith Moon, their drummer, with them. All of the profit that the Who made, or all of the revenue that came from the Who doing their US tour, basically went on hotel reparations for the damage that Keith Moon had done to hotels. So why on earth would bands still have drummers, especially in electronic music? I saw Depeche Mode last year. They had a drummer on stage. Prodigy, they have a live drummer on stage with an acoustic drum kit. Faithless, one of my favourite live bands, they have, there's so much percussion in there that they have 2 live drummers on stage. So with a live drum experience, you need to have, somebody banging these 7,500-year instruments, because that kind of makes for the atmosphere. We got in 1980, I think it was the TD-808, the first drum machine that all of the house musicians started at using the original one. We've had drum machines for years, and hopefully AI is not going to impact the fact that we still need to see live musicians and live DJs. So I got into something called Sonic Pi that I was using as you were coming in. This is basically an application where you can live code. So what you do is you basically create a loop, you put samples, you can put drum beats in the loop, and you can run that. And then you can modify the code and run it again, and the next time the loop runs, it will play the modified code. So you can basically live code complex music scenes. And it is a thing. There are DJs who are basically focusing on that. And I saw this in Dylan Beatty's session and started playing around with it for quite a while. And then I started looking at DJs. These guys are called DJs from Mars. They're Italian. And they put out a mix on YouTube where they did 100 festival anthems in 13 minutes, and they mixed all of the songs together. Originally, it was just a video showing all of the actual songs with the mixing together. And the comments were going on YouTube and saying, you can't do that live, that's just pre-recorded. There's no way anybody can mix 100 songs together live and do it live. So they did an actual live video of it, and I'll show that. I've got to be careful on the mute button because I don't want to F-bomb the session. That was why there was the the parental warning on there. I did mess it up at NDC Oslo. Oh, and also this is what they do. They're basically mixing everything live here. Let's start that again.
Sit, trash it, change it, melt, upgrade. Charge it, point it,
Put your hands up,
snap it, work it.
put your hands up for Detroit, a lovely city.
Technologic, technologic.
Put your hands up for Detroit, Riverside, mother.
So what they do is, this guy's playing all of the samples, the other guy's doing all of the music, and they're able to go through and just basically put those 100 songs together. I don't know how they do it, and they've got cardboard boxes on the head, so obviously the field of vision is going to be quite limited. But it's quite impressive what they put together. So I was wondering, well, can you do that in Sonic Pi? So I went and did this. I think this is it.
Buy it, use it, break it, fix it, trash it, change it, melt, upgrade it.
Put your hands up,
Charge it, point it,
put your hands up,
snap it, work it.
put your hands up for Detroit, a lovely city.
Technologic, technologic.
Put your hands up for Detroit, Riverside.
There it goes. Yeah. So they were doing something called key shifting, where in the mix what they can do is basically shift the keys of the songs and be able to make stuff blend together. So there's two things. I mean, that's fine. It's kind of a proof of concept that you can code a complex live set. But two things that are bad about that. One is it's static coded, and I wanted to do something where I can actually live code it. There is a thing where some DJs will do a pre-recorded mix, and they'll just play a big long, an hour-long MP3 file, and they'll wave their hands around and shout a lot. And it's meant to look like they're DJing, and it's considered bad practice to do that. Another thing is stealing other people's stuff, because DJs from ours have put that mix together. I don't want to just go in and take everything that they've done, all of their creativity, and just reproduce that myself. I wanted to come up with it with my own mixes. So this is kind of why I started getting into this particular project. So I'll jump back to the slides, and I'll talk a bit about how I'd created this. Now, initially, just about the decks that they use. This stuff is expensive, so that's a Pioneer CDJ 3000, which is that's in Swedish crowns, so it's probably about the same in Norwegian crowns. There's now a CDJ 3000X that's about 30,000 crowns, and they have 4 of those, and they have a mixer, so you got to pay tons and tons of money before you can even, that's before you've even bought any speakers and sound system. And it's expensive and it's big to carry around, so that's not really an option. So you can do that in Sonic Pi. You can also, I also got into music and looked at how we can classify music. I think I've got this video. And what I was doing was using classification based on the Mel spectrograms of music to be able to predict the genre of music. So this is another demo. Again, there's colourful lyrics, which I'll try and filter out here. So there's the brown one, which is jazz. Wasn't too good at that. It's a bit colourful, so I'll drop the volume down on that. But this is, you can see the purple hip hop is going up there. So I thought that was really good fun. I was using a vision model, and I trained it on the Mel spectrograms, which is kind of an image of the audio. and it's able to do that actual classification. So we can actually use models to understand about music. So I started looking at similar sounding beats. I thought, well, all I've got to do is to find music that sounds similar to other music, bang it into a vector search, and then I can start creating DJ mixes based on similar sounding music. So I took my MP3 collection. I started out using a VGG ISH model to get the embeddings, and I used, this comes later when I started getting into record box, but I basically initially started out looking at the first 30 seconds of the tune and finding similar sounding beats. So I can show you what happened with that. If I go into the embeddings project, I've got the similar song search. So this is similar to the dogs search. The only thing that I'm changing is I'm taking in music files and I'm doing my embedding, and I've got all of these stuck in Azure AI Search. So what I can do is I can, because they're in AI Search, I can actually do filter queries as well. So I'm searching where the artist is equal to the Prodigy, and this is finding all of the Prodigy songs that we've got. So if we take song 7, which is Voodoo People by the Prodigy, what I can do then is do the embedding on that song. I can then search for similar songs or similar sounding songs to Voodoo People by the Prodigy. Now this takes a while to run the code. The Azure AI Search is blindingly fast. The thing that takes time is just loading up all of these MP3 file players. So this is the song that I'm searching for, Voodoo People by the Prodigy. And the most similar song that it came up to is obviously Voodoo People by the Prodigy, because that's going to have a cosine similarity of 1.0. The next similar one was Disco 2000 by Pulp, and I thought that doesn't sound anything like Voodoo People by the Prodigy. And then we've got Lunacy Booth by Therapy, Grunge by the Dylans. We've got Veloria by the Pixels, the REM Radiohead, and even if you go way down the list, you've got Oasis and Sonic Youth, and Manic Street Preachers. New Model Army, they're from Bradford, where I grew up. And these are all songs that basically start with heavy guitars. So I'd solved that problem of finding similar sounding music, but then there was the mixing issue of actually mixing tunes together. I quickly realized that when you want to mix tunes that sound nice, you don't pick stuff that sounds similar, because you get mixes. So what you really want is kind of a blend of having the same types of chord progression, or the same type of percussion, the same type of notes, the music being in the same key. So I went away and I learnt a bit more about music theory and looked into finding how that could actually work. So there's something called the circle of fifths, which basically says that certain keys, certain major keys will work well with certain minor keys. If you play the piano and you play the scale of C major, this is the white notes from C going up to C. And then you play the scale of A minor. Well, that's the white notes going from A up to A. So C major and A minor use the same notes, and all of the complementary major keys will have a minor key. And DJs have turned this into the Camelot wheel. I still use G minor and B minor. Quite a lot of people do, but they have this 9A, 9B, and I never remember how these correspond. But if you're playing a song that's in G major, then you can mix to something in E minor or D major or C major, and there's a better chance of the sound mixing together. It doesn't always work, but that's basically the theory that goes on behind it. So you get into what's known as harmonic mixing, where you're picking two tracks that sound harmonically similar. So we've got Sweet Dreams by the Eurythmics and Enjoy the Silence by Depeche Mode. They're both in C minor. They're at different BPMs. So what you can do in Sonic Pi is you can kind of experiment and see if those songs fit together. So if I go to a new window and just, I don't want to do that one, that was something else I was working on. I can just take this one. And then if I just do for sample and we take Eurythmics and we take the vocals from Sweet Dreams. Now this is what's known as a studio a cappella.
Sweet dreams are made of the years. Who am
So it's the
I?
actual studio recording of Annie Lennox's voice. You do get AI that can split off the vocals from tracks, but it sounds pretty horrible, especially when you play it out loud on a good system. And that originally in the, was it 1981 or something, when Sweet Dreams was a single? Was originally played on top of this.
Sweet dreams are made of the years. Who am I to disagree?
And that just gets played so often in clubs. It's great that that song's lasted so long. But then you can go to Enjoy the Silence by Depeche Mode and find something from that. And I used synth track 8. So...
Sweet dreams are made of the years. Who am I to disagree? I travel the world
You
and
can
the
see there that those two kind of work well together. I messed that up actually. I thought I was in a loop, but I wasn't. So I'll just drop that back onto track 8. Yeah, I can probably do the whole thing if I just sleep for 32. 32 beats, and then we can drop on synth 9. So if I do that and that's going to be synth track 8, and I need to set it to 126 BPM.
sweet dreams are made of the years. Who am I to disagree? I travel the world and the 7 seas. Everybody's looking for something. Some of them want to use you. Some of them want to get used by.
Because those two sections are using, or those two phrases are using similar notes, then it kind of works. It sounds nice. And one of the things is when coming up with remixes is to be able to take the a cappella from one song and put it onto a completely different song. And that's a lot of what DJs from Mars were doing to create their mix. They always had at least 2 songs playing, layering on top of one each other. But finding those combinations is really, really time consuming to do manually. So I wanted a mechanism that I could use for being able to find matching phrases. So what I do is I've taken MP3 samples, I put them into DJ software, which is Rekordbox. And I did play around in Python trying to extract the keys and the phrases and the BPMs, and it was horribly complex, and I didn't really do a very good job of it. But what Rekordbox is able to do when you push in all of your MP3 files or all of the music that you get off a streaming service, it does the analysis on those. So if I go to playlists and in tracks, I don't know if I've got Sweet Dreams in here. We probably have somewhere. Yeah. So what it will do is it will get the beats per minute of the song. So that's 125.2 BPM, and it's in C minor. And you get all of different sections like the verses and the choruses. And if it's dance music, if I search for deadmau5, for example, there you get all of these kind of rises and drops in dance music. So it shows all of the up sections, so you know what sections to work on. Now, the record data box is encrypted. And also, they do really evil things like the waveforms. They put XOR masking on the waveforms to make it really difficult to read. But thankfully, a lot of clever developers have spent their evenings and weekends reverse engineering it, so you can get all of that information out of Rekordbox using a couple of libraries. There's a Java one and there's a Python library. So what I do is I feed the information into Rekordbox. I get out the metadata. There we can get the phrases, we can get the tracks, and we can get the waveforms. And what I do is I do the actual embedding on the phrases. But instead of doing it for similarity, I do something that's known as harmonic embedding. It's not actually machine learning. It's really just looking at the frequencies that are used in a particular track and getting a numeric representation of that. So if I just open the drop the bass section, I can show you a bit on how the music theory works for that. So what this is doing, I've got everything running in Jupyter Notebooks. So what I can do is run this. And this is showing my playlist. So if we go down and pick Alan Walker this time, Better Off Alone. We get the musical phrases from that. And this is basically showing the waveforms, and it's all split by all of the different phrases. So
This could be a good night for good times and you.
So that's a 32-beat phrase. And what I can do then is analyze section with the ID of 1. So that's that one. When we analyze the phrase, we get two things. The first thing that's going to pop up is the melodic spectrogram. And this is what I was using to classify the music. It's basically showing all of the kind of beats in the music. Very often when I'm playing a DJ set, I stick it into Audacity. And then you can switch from a waveform to a mel spectrogram, and you can see all the different sections in the track where the rises are and the drops and where all of the drum beats kick in. And this is the chroma filter, so if I play it.
This could be a good night for good times and you. Look like a good time. We're dancing to dancing in the moonlight. Now I want you back. Can you make me feel better?
And this is irrespective of the octave. I think that it's very heavily biased on the bass. There's quite a very, very deep bass in there, but that's showing the actual notes from the bass. Now, if we embed this, we can then search for tracks that are going to have similar embeddings or a similar set of notes to that particular. It's kind of like finding a song with a similar chord progression. And then we can mix those together and see how that works. So I can't remember if there's anything more on the slides showing how that was working. Oh yeah, this is a bit about the process. Yeah, that was the actual process. And so I was just extracting the phrases programmatically. And this is the information that I put into search. So we've got the beats per minute. We've got the label, which is that's an intro. And then there's the rises and the drops and choruses and various things like that. And all of the information about where it is appearing in the song. And then that is going to be embedded and put into AI Search. I'm using the information from the chroma filter to actually embed that. And then we can search for similar tracks. So if I want to do that, then I've got these. I actually have still got all of this stuff running in Jupyter Notebooks. I can go into the sample mixer. And what this will do is it will show all of the samples that I'm actually using. So what I've done is I've extracted lots and lots of different sections from different songs I can use within Sonic Pi. So hopefully this is going to run when I run it. So we've basically got 632 samples in the index, and I can select something. I've put some things that actually work quite well in here. So there's Rihanna, We Found Love. So if I drop to that one. And again, I've got a studio a cappella for this, I think. Or have I?
Yellow diamonds in the light, and we're standing side by.
So if we want to find something that musically will go with that particular track, then I just put in section 2. And I've got the options here. Do I want to go for the same key or any key? Or do I want to take the vertical keys in the Camelot wheel or the horizontal keys, or both the vertical and horizontal? That's just using filtering based on the key. And if I just keep it within the same key, it comes up with all of the tracks that should work, and it automatically generates mixes of them as well. Unfortunately, it's not displaying that waveform, so you don't see it. So it's recommending Fade Into Darkness by Avicii.
Yellow diamonds in the light, and we're
And then Breeze by Ferrin and Lowe.
yellow diamonds in the light, and we're standing side by side as the shadow crosses mine. What it takes to come alive. Yellow diamonds.
So that means you can take We Found Love by Rihanna and you can turn it into a progressive trance song by dropping on that those actual tracks. And that's one of the things that I've do at one point in the mix. And I just think it's fun to play around with this. Oh yeah, Coldplay as well.
Yellow diamonds in the light, and we're standing side by side as the shadow crosses mine. What it takes to come alive.
So again, that really changes the characteristic of the song by putting different sections onto it. So it's been a really fun project. As I mentioned, this takes an unhealthy proportion of my free time. I've got like 5-hour train journey running back. So I'm going to be, playing around with that on the way back. My train journey here, I was just frantic preparing labs and sessions and stuff. I do have to do a bit of the beat shifting because all of the songs are in different BPMs. Unfortunately, in Sonic Pi, you can't do beat shifting and key shifting if you're working in something like Rekordbox. And this is a free download, by the way, so if you do want to download it and play around with it. So what I can do is if we drop in, say, Aural Synapse by Deadmau5, we go to this section here. I need to put this onto the speakers, actually. Bird's Dog. Oh, yeah, that seems correct. And what this you can do is you can shift the tempo. So you can speed it down, and that's not going to have an effect on the pitch. You can also shift the key. And that's done using maths and audio processing. You can't do that live in Sonic Pi yet. I wish you could. It would be much more versatile. But there is a software called Rubber Band from Python that allows you to do key shifting and tempo shifting. So I've shifted everything to 126 BPM. Sometimes it sounds a bit bad if it's speeded up too much or slowed down too much. The original trance song Breeze was about 140 BPM, so it does sound a bit different when you move it. And I'm just using Azure AI Search to be able to make those mixes. Stuff I want to work on in the, so I've demoed that. I did have a few challenges running through the implementation of this. One of them was my hard drive space. I think I've got close to 1 million MP3 files on my hard drive at home. I'm going to buy a new hard drive just for the purpose of doing that. I've now got into looking at DJ mixing, so you can take an hour-long mix, and I want to analyze the mix and figure out what they're doing on the mix. I've got 1,200 one-hour-long Tomorrowland mixes, and I'm working on downloading. BBC had something called the Essential Mix on Radio 1 that's ran from 1992 up to today, and they do like a few hours a week of just having a DJ mixing there. So there's a few thousand hours of stuff there that I can look at there. It's got a lot bigger than that currently, but there's a lot of files there. And band names as well. Again, Dylan Beattie is saying that there's all kinds of things in the band names. These are all different characters, and this was driving me nuts because MP3 files typically use the artist, and then there's a hyphen, and then there's a band name, or there's a minus sign, or there's a non-breaking hyphen, or there's an N dash, or there's an M dash. So just actually splitting out and analysing the tracks was causing all sorts of problems. And then the names, back when I was a kid, they had Blur by, Parklife by Blur or Wonderwall by Oasis, but that was the longest one that I managed to find in the EDMs. The actual band names are long. And then featuring is always spelt differently as well. Sometimes it's capital S, sometimes it's F-E-T, sometimes it's F-E-A-T with a dot, and it was messy. More research. There is a data set called, Chordonomicon, with 666,000 chord progressions in it that you can use to analyse. That looks interesting to play around with. There's a white paper on detecting drops in EDM, and that's another resource that I can look at as well. Also, there's a fantastic website which is called Every Noise at Once. And this was put together by somebody who worked at Spotify. And the idea is that you can select a music genre, and there's all kinds of music genres. I don't know if there's any Oslo. Oops, Control F. I don't see that. Oh, it's Norwegian pop, Norwegian indie. So you go to Norwegian indie, and it's going to give you examples of that genre, and we've got lots of bands that are classified as being Norwegian indie. So I screen scraped that website, and there are 463,000 30-second MP3 samples which I downloaded. I put them into Rekordbox. It took 3 weeks to do the actual beat embeddings, and then I embedded them, which took another few days. But I've got that search index, and I didn't do all of them. Sometimes it doesn't detect the BPM, but we should have Every Noise at Once in here. Where is it? Oh, this is it, yeah. 298,000 MP3s that we've got there. So I can actually do mixing against that. I haven't had much success with it. It was only before I jumped on the train here So I can mix the samples with every noise at once, and it is a bit weird. So let's pick, let's go for Alan Walker again. Better Off Alone.
This could be.
And if I just take sample 1 and we just go for 50 mixes, and I'm picking the same key. And then if you want to mix Alan Walker with Swedish emo or Alberta country, German hyperpop,
Don't need no
anything with vocals isn't going to work, but maybe there's some, Peony EDM. I want something without vocals. I don't know if I'm going to find any. I'm guessing if it's known as crate digging when you kind of hunt around to find these rare tracks. If I've got a 5-hour train trip, maybe I can find some really bizarre mixes that nobody's ever done before there, and that's going to be fun to look at. If you're interested in the coding with music, the goddess of all things relating to that is DJ Dave or Sarah Davis. And I'm really not doing that much with Sonic Pi, but when you look at what DJ Dave can do, I'll just find some stuff to finish off with. This will be the last video there. If we go to her YouTube
Winter
channel,
for many of
a
us.
short video just showing this.
Here is what it sounds like with a 4 on the floor. So I have this arpeggiator that's running through a sequence of notes or chords, and it's using a supersaw sound. And I have the envelope set here, and also a low pass filter envelope that's on a slider. So if I change the slider, it's going to make it sound brighter. And then I have a similar setup on this bass line up here, where I have the low pass filter slider set pretty low so it sounds more like a bass, but it's using the same sound and it's running through just a different sequence of notes. And then on both of them you can see I have post gain set to a variable. So that variable basically makes it possible for me to sidechain these sounds to a kick drum. So if I bring those patterns in, it's also going to bring the kick drum in. And here is what it sounds like with a 4. Here is what it sounds like with a 4 on the floor.
So if you ever looked at working with electronic music, you probably recognize like arpeggiators and side chaining and post gain and filters and all this type of stuff. Sarah's doing all of that in code, and she's performing live as well. Where was it?
Here is what it sounds like with a 4 on the floor.
If we go back to the channel and to the videos, this was from 3 weeks ago. It's probably going to get a YouTube advert about AI and music, but this is. Concert. So you can do all kinds of stuff with this music through code. I do recommend checking out. It's good fun. Thank you very much for listening. I'll be around a bit for questions until the afternoon, and then I'm going to jump off for my train at about 4 o'clock. Thank you very much, and enjoy the rest of the conference.